Welcome to the Explainer. Today, we are opening up the hood of artificial intelligence. When we talk about AI, we usually focus on the mind-blowing stuff, right? Passing the bar exam, generating incredible art, or driving cars completely autonomously. But underneath all of that apparent magic is a really beautiful, deeply spatial world of mathematics. So our goal today is to look directly into that engine room to discover the elegant linear algebra that literally powers everything we call deep learning.
It's kind of the core question of our era, isn't it? When a computer learns to recognize a human face or, say, translate an entire novel from English to Japanese, what is actually happening inside the machine? Well, it isn't magic, and it definitely isn't a human brain. It is, fundamentally, a mathematical optimization problem. But to really understand how it learns, we first have to wrap our heads around the sheer scale of the information it's dealing with. Take the famous MNIST dataset, for example. We're talking about a collection of 70,000 handwritten digits. Every single one of those digits is an image made up of hundreds of tiny pixels. If we want a machine to identify those numbers, we're asking it to look at thousands of training samples and somehow organically find the underlying pattern. We are asking it to literally weigh different pixels against each other to figure out what makes a 7, and a 3, a 3.
To figure out how it does that, here is our roadmap for today. 1. Demystifying deep learning. 2. Inside the neural network. 3. Matrices as the core engine. 4. Reimagining multiplication. And finally, 5. The 4 fundamental subspaces.
All right, let's jump straight into part 1, demystifying deep learning and the ultimate goal of AI.
Mathematically speaking, the whole game is about constructing one single learning function. Let's call it f of v. The input, v, is our data, like those handwritten digits we just talked about. This function learns exactly what to look for by assigning weights to different parts of the input to classify it correctly. But here is the catch, and it's a big one. We don't just want it to memorize the training data. That's a trap called overfitting. Our function absolutely must learn the underlying pattern so well that when we throw entirely unseen test data at it, it generalizes and still gives us the right answer. Moving on to part 2, let's look inside the neural network at the actual architecture of learning.
Picture the flow of information for a second. You've got input samples pouring in on one side, filtering through a series of interconnected hidden layers in the middle, and finally popping out as a classification on the other side. In a fully connected network, every single one of those connections between the layers represents a specific weight that the computer needs to learn and optimize. The sheer number of these hidden layers is exactly what makes deep learning so incredibly powerful.
Deep learning sounds intimidating, but it's honestly just a stack of very simple steps layered on top of each other. First, we start with our input vector, v. Next, we multiply it by a matrix of weights, a, and add a bias vector, b. That's called an affine function. Third, and this is super important, we apply a nonlinear activation function, like ReLU. And finally, after repeating that whole cycle across multiple layers, we arrive at our output layer, W. Now, here is the absolute crucial difference to understand. Linear versus nonlinear learning. Affine linear functions alone are incredibly fast, but they're just too simple. If you only use linear functions, your network is kind of stuck. For instance, it couldn't separate data points inside a circle from points outside of it. It just draws straight lines. But the moment you insert a simple nonlinear function, specifically the ramp function called ReLU, which just takes the maximum of 0 and x, boom, you get true deep learning. It allows the function to bend and fold and mold itself around highly complex, messy real-world data, like the unique contours of your face for Face ID.
Okay, part 3, matrices, the core engine and the mathematical pillars of the entire system.
The mathematician Gilbert Strang really hit the nail on the head when he said, linear algebra has moved to the center of machine learning, and we need to be there. Because behind all the perceived magic of AI are the rock-solid pillars of linear algebra. Every single weight, every input pixel, every bias vector, they are all, without exception, organized into matrices and vectors. If we want to understand machine learning, we literally have to understand the matrix.
This brings us to part 4, reimagining matrix multiplication and moving way beyond just the basic calculations.
If you've ever taken a linear algebra class, you probably learned to multiply matrices using inner products, crunching a row times a column to spit out a single number. And that is exactly how computers compute, because it's super efficient for them. But for high-level human understanding, we need to completely flip the script and look at outer products. This means multiplying the columns of the first matrix by the rows of the second. When we do it this way, we realize that a full matrix product is actually just the sum of simple rank 1 matrices. It completely changes how we visualize the structure of the data itself. Which leads us perfectly to the concept of rank. You can think of rank as essentially the DNA of your data matrix. It tells us how much truly unique, independent information is actually packed in there. If a matrix is full of redundant data, its rank is low. And here is one of the most beautiful theorems in all of math. The number of independent columns in a matrix always, and I mean exactly always, equals the number of independent rows. Row rank equals column rank always. Why is that such a big deal? Because it proves that no matter how we slice the data, its core informational density remains perfectly identical.
And finally, part 5, the 4 fundamental subspaces and the actual spatial geometry of data.
Here's the wild part. Every single matrix ever created generates 4 fundamental subspaces. You have the column space, which contains all combinations of the columns, the row space, which has all combinations of the rows, then there's the null space, containing all the solutions where the matrix times a vector equals 0. And finally, the left null space, doing the exact same thing for the transpose matrix. These 4 spaces act as the ultimate organizational framework for literally all linear equations in an AI network.
And the coolest part is that these spaces actually exist geometrically as perfectly perpendicular dimensions. The row space and the null space sit perfectly perpendicular to each other in one dimension, while the column space and the left null space are completely perpendicular in another. Together, they capture absolutely all possible combinations and solutions, so whenever a neural network optimizes its weights, it isn't just crunching numbers, it is physically navigating its way through these mathematical spaces to find the absolute perfect fit for the data.
It's honestly a marvel when you step back and think about it. We've gone from analyzing 70,000 simple handwritten digits to autonomous vehicles and generative AI that can write code, and it's all powered by the exact same atomic structures: columns, rows, outer products, and fundamental subspaces. By understanding the linear algebra under the hood, you don't just see how a machine learns today. You kind of have to ask yourself, if these basic geometric building blocks power today's AI, what kind of incredible, totally unimaginable architectures is this math going to unlock tomorrow?